You gotta do that. You gotta make sure you saw your coded style.
Okay, awesome. Hi. Hello. Welcome to the CBE review. Okay, yes. My name is India Evans. I'm a recitation leader for Dr. Greg Wheeler. My other recitation leader who will be leading this with me has a class right now. She will be here 30 minutes, so she'll lead the second half of this. But her name is Emily Nielsen. She's also a recitation leader for Dr. Greg Wheeler. Okay? Okay. Just to let you know, this is being recorded. None of your faces are being recorded, but only your voices will be recorded if you ask a question or answer a question. But just a heads up, we won't be saying any names if we call on you. So just so you know, your voices will be recorded. And you are welcome to review the video after this on our Aggie Math YouTube channel. That's where we post the recordings. Okay? Okay, let's get started then. I'm going to close the door a little. I guess. Okay. Okay, awesome. Okay, so here's what we're going to go over. CBE 2 covers lessons 7 through 10. We talk about circles, we talk about transformations of functions, combining functions, and we talk about inverse functions. Okay? Okay, so transformations of functions. We talk about shifts, stretches, compressions, and reflections. Okay. I do not care. Okay. Vertical transformations. If you have a vertical transformation to your graph, it is going to affect the function, the parent function f of x, like this. If we have a vertical shift, we're going to add k, however many we move up, or subtract k, however many we move down. Okay? And that's from our parent function f of x. For a horizontal transformation, we add the shifting, the part that's shifting, directly to the x in the original parent function. Okay? That means it's not outside of the function. That means it's affecting the x's directly. If it's outside of the function, then it means it's affecting the y coordinates directly. Affecting the x directly, it's affecting the x coordinates directly. The x's are a little bit weird. If something is affecting the x directly, so like this x minus h, or this, where is it? I guess it doesn't have it listed. But if it was a scalar affecting the x directly, it would do the opposite of what you think it's going to do. Okay? So x minus h means you're moving to the right h. Even though it says minus h, you're moving to the right h. It affects the x directly. Okay? And it does the opposite of what you think. If we had an x plus h, we would be moving to the left. We would be moving the parent function to the left. Okay? Okay, so it does the opposite of what you think when it's affecting the x directly. Everything except the reflection, because the reflection, there's really no other way to do it. Okay, so a vertical reflection. Again, if it's affecting the y coordinates, which a vertical reflection does, it is going to be on the outside of the parent function. Okay? That flips it across, flips all the y components across the x-axis. So it takes your positive y values and makes them negative. Okay, a horizontal reflection. Horizontal reflection, again, affects the x directly, but there's really no other way to think about it, so it does what you think it does. It just flips the x coordinates across the y-axis, so the positive x coordinates become negative x coordinates. We have a vertical stretch. Again, it's affecting vertically, so it is going to be outside of the f of x, not affecting the x, because it's affecting the y coordinates. This will stretch it by however much a is. So if a is 2, and you have a parabola of, let's say, y equals x squared, we know we have special points here at 1, 1, negative 1, 1. If we multiply this parent function by 2, we're going to get 1, 2, negative 1, 2. So it stretches it up. Okay? It multiplies all of the y coordinates by a. And then for vertical compression, we have 1 over A. It's going to just compress by that factor of A. So if we look back here, let's say we compress, so we multiply by a factor of 1/2, then we're going to get 1/2 and -1/2. So I will compress it. Okay. Okay. It doesn't have it listed up here, but if you ever run into something where it is saying A of X in here, it does the opposite of what you think. This is not going to stretch it horizontally. This is going to compress it horizontally. So it's going to compress it like this. And then same if you have Y is equal to F1 over AX. This one is going to stretch it horizontally. Okay. Yeah, and it just does the opposite of what you think, specifically with how we put in X values. If you draw out, let's say we want to shift Y equals X squared to the right 1, then we're going to have X minus 1 squared. We're shifting to the right 1 from our parent function X squared. And this is because if we draw out a table, we have 0, 0. Then we have 1, 1, and then we have -1, 1. And with our new function, with X minus 1 squared, we have 0 shifted to the right 1, but still going to have the Y coordinate of 0. And then we have 2, 1, and then we have 0, 1. Right? It shifts them all to the right 1. So we see if we plug in 1 here, we're going to get 1 minus 1 squared is 0 squared, which is 0, which is exactly what we want here. We get 2 minus 1 squared is 1 squared, which is 1, which is exactly what we have here. And 0 minus 1 squared is -1 squared, which is 1. So that's exactly what we have here. Okay? It's because we're putting them in as inputs first, instead of affecting the outputs, is why it does the opposite of what we think. Because we're saying, hey, let's take this value of 1, but let's give it the value of 0 in our original graph. In order to do that, we have to have a value of 1 originally, and then we subtract 1 from it to get back to our 0 of our original graph. That's why. It is the opposite of what you think. It's a confusing concept, but just remember, affects the X directly, does the opposite of what you think, affects the Y, does what you think. Okay? X's are in our F X minus H, that affects the X directly. So they're going to be of that form if they affect the X directly. Okay? Any questions on this? Yes.
What if you have an A on the outside and on the inside?
It's going to affect both. Yeah, it's going to, if you have an A, F, A, X. Yeah. You typically want to do what's affecting the X first. So it's going to compress it horizontally by A, and then it's going to stretch it vertically by A. It's hard to picture unless you use a table, but yes, that's what it's going to do. It's still going to do both of those things. Any other questions? Okay, awesome. Okay, common parent graphs to know. These are the parent graphs that you will typically use when asked to perform linear transformations on graphs. We have y equals x, the classic y equals x x squared, y is equal to x cubed, y is equal to square root of x, and then y is equal to the absolute value of x. Okay? Good points, good general points to know on these graphs are just like 0, 0, and then you know that you're going to be A for some point A. You're going to have the same points there. For y equals x squared, good points to know are 0, 0, 1, 1, 1, -1, 1. And then we have 2, 4, and -2, 4. Okay, these are good points to know if you're comparing a graph with its parent function. Okay? Okay, and then on x cubed, we have 0, 0, 1, 1, -1, -1. On the square root, we have 0, 0, 1, 1, and then we have 4, 2. And then on this one, it's just you're going to have A on this side, and then you're going to have negative AA on this side for any point A. Okay, so those are just good to know in case you're comparing a graph with its parent function, because then you can be like, oh, this point that I know is on the parent function has moved to the right, so I know that there's a shift to the right, stuff like that. Okay, any questions on the parent graphs? Okay, awesome. Okay, cool. We're going to look at problem 1. Okay, so we're going to write the equation for the graph. Okay, first step, we're going to identify the parent graph. Okay, comparing this graph here that we have to our parent graphs on the last slide, which is this parent graph? Which is its parent graph?
Square root.
Square root, yep. We have a function that looks like this, which is our only parent graph that looks like that is a square root function. Okay, and you shouldn't get any other problems with parent graphs other than those, okay, on the CBE. Okay, so then we want to identify transformations, okay? So our original parent graph, I'm going to draw it up here. Remember, we have a point at 1, 1, then we have a point at 4, 2. Okay, so with transformations that we can see, taking just these points, we see that 0, 0, our point 0, 0, is now moved down to negative 4, negative 3. Okay? So now we know that we have shifted left by 4 and down by 3. Okay? Okay. If we come over to this next point, we still have a point. It goes 1 over and 1 up, just like this one. This point goes 1 over and 1 up. Okay. So what we can tell here, we can even check over here. This one goes 3 over and 1 up, just like this one goes 3 over and 1 up. So what we can tell with that is that there's no scalar affecting it. No scalar inside or outside, because these points are still the same length, quote unquote, away from this original point. Okay, so there's no scalar affecting it on the y or on the x. Okay, so all that we have is that it's shifted left and down. It's not flipped horizontally. It's still the same parent graph. So it looks like our parent graph in the same direction and everything, so it's not flipped. Okay, so in this case, we're going to say we have x is equal to f of x. So then we're going to have a f of x, this is our new function though, f of x, a x minus h, let me put bx minus h, and then plus k. So our h is our shift horizontally, our k is our shift vertically, our a is our compression or stretch vertically, and our b is our compression or stretch horizontally. Okay? I already clarified that we do not have any compression or stretch, otherwise these points would not be the same distance away as they are on our parent graph. So we know that a has to just be 1 and b has to just be 1. There's no scalar. There's no scalar affecting it. Okay. But we do have a shift to the left by 4. So this h is going to be negative 4. We shift left 4. And our k, we shift down 3. So we're going to get k is equal to negative 3. Okay? Compare the original points with your parent function. Okay. So our final equation is going to be f of x is equal to x minus negative 4 is plus 4 minus 3. Okay. And we can see right there the fade-in solution. Perfect. Any questions on this process? Okay, great. Yeah, just make sure you know your points on your parent function because they are very helpful for doing problems like this. Okay, now here we're going to graph the function, okay? Okay, in this case, what's our parent function? Yeah, y is equal to x squared. That's our parent function here. Okay. Okay, in this case, because we have a scalar out in front, I'm not going to just put the parent graph and then do alt shifts. I'm going to write out a table, okay? Okay, so in our original function, x squared, our x and y values that are known are 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. We'll just stick with those, okay? Okay, awesome. So what I'm going to do first is I'm going to do what's affecting the x first. I'm going to do that horizontal shift. So we now have x plus 4 squared. This affects the x's only, so our y coordinates are still going to be the same. Okay. And x plus 4 means we shift to the left 4. So we're going to subtract 4 from each of these. So we have negative 4, negative 3, negative 5, negative 2, negative 6. Okay? Okay. Then what I'm going to do is I'm going to multiply by the scalar here. So now we have 4/3 x plus 4 squared xy. Okay, this is affecting, it's not inside with our x, so it's affecting the y coordinates, not the x coordinates. Okay? So we have still the same x coordinates, negative 4, negative 3, negative 5, negative 2, negative 6. And then our y coordinates all get multiplied by that scalar of 4/3. Again, we're affecting the y coordinates. It does what we think it does. Okay, so it's just going to be plain multiply all the y coordinates by 4/3. Okay, so we have 0, we have 4/3, 4/3. Then we have 16/3, 16/3. Okay, okay, and our last step is to just shift it down 2. Okay, so 4/3 x plus 4 squared minus 2 xy. The vertical shift of negative 2 is affecting our y coordinates only, so we can write down our x coordinates. And then we have 0 minus 2. Then we have 4/3 minus 2, which is 4/3 minus 6/3, so negative 2/3. Then we have 16/3 minus 2, so 16/3 minus 6/3 is 10/3. And those will be our points on our final graph. Okay? So we can graph that out. We have the vertex at negative 4, negative 2. Then we have negative 3 at negative 2/3. So that is going to be somewhere right there. Then we have negative 5 and negative 2/3. Then we have negative 2 and 10/3. Yeah. And 10/3, so 10/3 is sorry. Thank you. That's like 3 1/3. So negative 2, 3 1/3 is like right here. And then negative 6, 3 1/3 is like right here. Okay. And you do not have to start with these points. I started with those points because those are the points I told you guys at the very beginning. You do not have to start with them. You can pick different points. Okay. That way you don't have to graph fractions. Okay, you can pick different points. But that's what our graph should generally look like.
How do you know which points to choose, I guess?
Well, you can either choose the points that are typically associated with the parent graph, which are the points I did choose, or you can choose points.
Are those always going to be the same ones then for like the x squared graph or whatever? Like those points you just presented?
Yes, but you can also choose points. You just have to figure out what, if you choose an x coordinate, what the y coordinate is. Like if you chose 3 as your x coordinate, then on our original parent graph, that y coordinate would be 9, right?
Because you're just plugging it into the x squared.
Yes, yep. So then up here on our table, we would then add 3 and then 9. And then you could do this. And in this case, once you multiplied, because you would still have that 9 over here. And in this case, once you multiply that 9 by 4/3, you would have
63 over.
why can't I do math? Times 4/3 is going to be 9/3 times 4. So 3 times 2 is going to be 3 times 4 is going to be 12. So then you have 12 over here, which is not a fraction. You can choose points like that. Just make sure you're getting the original points in the parent function and then using your shifts correctly. But yes. Yeah. Any other questions?
I guess you said to choose different points so you don't get these fractions, but I mean, obviously you can only graph the whole numbers on like the practice test or anything.
Okay, yeah, so then you're gonna
you
want to
just
do
choose
it.
a point until you get a whole number, or
What I do
That's what I did.
if you look, throughout all our steps, all our y coordinates stay the same until the step where you multiply them by 4/3. Then they change into something else.
Right.
So in order to get a whole number out of this step, I would choose a whole number that would cancel out that denominator. So a 3 or a 9 or a 6, stuff like that. I would choose that as output. You then just have to find the right input. Because like 6, your input's going to be square root of 6, which is not helpful. But 3 gives you 9, which is divisible by 3. Stuff like that. I would say, yeah. You only need to graph 3 points for a parabola. So you could choose 3, 9, negative 3, 9, and then the 0, 0. And then go through all that, and you should get whole numbers out. That's my recommendation. Just look for where the y coordinates change. Then choose whole numbers based on that. Find the inputs based on those. Yes. Okay. Any other questions? Okay, awesome. Whoa. Okay, you can barely see the correct graph they put over here, but that looks very similar to our graph. So we're good. Okay. I'm sorry, I do not know how to erase on this thing. Maybe. No. Oh, there we go. Okay, awesome. Okay, moving on. We have the graph of the equation y equals fx is shown. We want to graph the equation y is equal to negative f 1/2 x plus minus 2. Okay? Okay, so in this case, I'm just going to write out all of our x, y coordinates for these specific points that are graphed. We have negative 6, 3. Then we have negative 4, 6. And then we have 2, 0. Okay? So 2, negative 4, negative 6, 0, 6, 3. Okay? Okay, we're again going to take this step by step. Let us start with what's affecting the x first directly. Again, does the opposite of what you think it does. So instead of dividing by 2, we're going to multiply by 2, all the x coordinates. So we have f of 1/2 of x here. Our y's are untouched. This is affecting the x's only. And then we are multiplying all the x's by 2, not by 1/2. It does the opposite. So we have 4, -8, -12. Okay, then I'm going to do the scalar out in front that's affecting the y-coordinates. That's -1. So it does what we think it does. It's affecting the y-coordinates and not the x-coordinates. So our x-coordinates are unchanged. And then our y-coordinates are multiplied by -1. So we have 0, -6, and -3. Okay. Okay, and then over here, x, y, we're going to do our last step. We're going to shift it down 2. So our x coordinates are unchanged. It's affecting the y coordinates. Shift it down 2. So we just subtract 2. It does what we think it does. -2, -8, -5. Okay. So on a graph, all the way up there. And then we have 1, 2, 3, 4, and we come down 8. And then, yeah. Okay, so we have the point 4, -2. It's like right here. Then we have -8, -8. Like right there. And then we have -12, -5. Like right there. Okay. Yep. And then we have the solution points right there. -12, -5, -8, -8, 4, -2. Any questions on that? Okay, cool. Okay. Then we will move on to circles. Yay, I love circles. Okay, so we're going to talk about the equation, stuff you can expect. The typical equation of a circle is x minus h squared plus y minus k squared is equal to r squared. Okay? And this is where the point h of k is the center of the circle. So h is the x coordinate of the circle, and k is the y coordinate of the center of the circle. And then r is the radius of the circle. Remember, r is the radius. I know it's a really common mistake to, when you're writing out a circle equation, to just put r on the side. That would not be correct. You need to square that r. Okay? Okay. Yeah, any questions on the equation of a circle?
Are you still flipping it? So like x minus 5, would that be a positive 5 on the graph?
Yes,
Okay.
it's x minus h, where h is our x coordinate. So if h is a negative number, then it's going to be x plus that negative, or the positive of that negative, right? X minus -5 is x plus 5, okay? And then same for the y. In this case, the y will also do the opposite of what you think it does, okay? If you have a positive, it is going to subtract that number for the center of the circle, okay? And that's because it's inside this x squared. It's technically its own function. So it does the opposite of what we think it does. Okay? Any questions?
What would happen if you changed the exponent power?
The exponent power, it wouldn't be the equation of a circle anymore. Yeah. So I don't know, because then there would no longer be a center of the circle. So there would no longer be a k necessarily. Yeah. If we got rid of both of them, it would just be the equation of a line. You would bring everything over until you leave y alone. That would just be the equation of a line. Yeah. Okay. Okay, so graph the circle defined by the equation x plus 2 squared plus y minus 3 squared is equal to 9. So again, we have x. Whoa, I just messed up. What the? Okay, whatever. I guess I'm not getting the eraser. X minus h squared plus y minus k squared is equal to r squared. Where h, k center, and r radius. Okay, so what we want to do first of all is we want to identify the center, identify the radius, and then we want to plot the points, and then we want to draw the circle. Okay. Okay, in this case, our center is h of k, and we see that we can find h and k from this equation directly. We have x plus 2, which is x minus negative 2. So we have h is equal to negative 2. We have y minus 3, so y minus positive 3. So k is equal to 3. And then we have r squared is equal to 9. So if we take the square of both sides, we get r is equal to 3. Don't take the negative of that square root. You can't have a negative radius. Okay? So it gives you the positive radius of 3. So we know that our center is at negative 2, 3, and our radius is 3 units. Okay? So graphing that, we come over to negative 2, go up to 3. That's our center. Then we know that on all sides of the circle, every point on the circle is 3 units away. So we can graph the easiest ones. We can come over 3 units, 1, 2, 3, and then go left 3 units, 1, 2, 3. And then you can even go up and down 3 units, 1, 2, 3. And then we can connect the points. That was really poorly drawn, but yeah, there we go. Okay, and we can see in the solution negative 2, 3, and radius of 3. Any questions on that? Okay, awesome. Great. Okay, the distance formula. Okay, the distance between 2 points, x1 and y1 and x2 and y2 is given by the following formula. Note that the distance is the same irrespective of the order. So that means you can take x squared minus x1 and you'll still get the same thing out. Okay, because it's just the distance. It doesn't matter which one comes first in your head, because on a graph the distance doesn't care about which one comes first. Okay, so yeah. This is the distance formula. This comes from the Pythagorean theorem, where we have 2 points here and here. This is going to be, let's say, length A and length B. And then we have the hypotenuse. And we know that A squared plus B squared is equal to C squared. So if C is that hypotenuse. Okay. And if we square root both sides, we get a squared plus b squared is equal to c. So if we have 2 points here, we know their distance from here to like the x-axis, let's say. That's going to be the difference between the y-coordinates. And the difference over here, that's going to be the difference between the x-coordinates. So then the length is the distance between the y-coordinates, and the length here is the distance between the x-coordinates. We add those together, squared, and that is equal to the distance between the actual 2 points. That's why we have the distance formula. It's from the Pythagorean theorem. Okay, but yes, that is the distance formula. Any questions on the distance formula? Okay, awesome. Okay, the midpoint formula, the midpoint of a line segment with endpoints at x1 and y1. So x1, y1, and x2, y2 is located at the point indicated by the formula below. You basically just take both x-coordinates, add them together, divide by 2. Because if you divide those x-coordinates by 2, then you're going to get like right here. And then you take the y coordinates, divide them by 2. You're going to get like right here again. Okay, so that's going to be the distance of the midpoint. Any questions on the midpoint? Okay, this is going to be helpful when we have harder questions with circles. So we want to write out an equation for the circle that contains a diameter with endpoints -3, -1, and -5, -3. So if we graph this really quick, we have a point here at -5, -3, and we have a point here at -3, -1. So our circle is going to look something like this. Okay? We're given a diameter, not the radius. So we first want to use the midpoint formula to find the center. We have this line that connects the diameter endpoints. We want to find the midpoint of that because the diameter is 2 times the radius. So the midpoint will have half of the diameter on one side, half the diameter of the other, which is the radius on one side, radius on the other. So that will be the center. Okay? So we want to use the midpoint formula to find the center. So we have x1 plus x2 over 2, y1 plus y2 over 2. Okay, so we have -5 plus -3 divided by 2. And then we have -3 plus -1 divided by 2. -5 plus -3 is going to be -8 divided by 2, which is going to be -4. -3 plus -1 is going to be -4 divided by 2 is going to be -2. Okay, so that's going to be our center. In other words, that's going to be our h and our k. And now we want to use the distance formula to find the radius. Okay, so we want to find the distance formula to find that length of the diameter first. So we have x1 minus x2 squared plus y1 minus y2 squared. So we have -5 minus -3 squared plus what is it? Oh, you know what I'm going to do actually? It's so stupid that it doesn't give me the eraser. Hi, Emily. I'm going to use the center points instead, because that will give us the radius directly. So I'm going to have -5 minus -4. Then I'm going to take -3 here minus -2. Okay, because we have this point now. We know this point is a radius length away from this point. So if we find the distance between those 2 points, we find the radius, right? Between the center and one of the diameter endpoints. So -5 minus -4 is going to be -5 plus 4, which is -1 squared. So we have 1 plus -3 minus -2. That is going to be -3 minus -2, -3 plus 2, which is going to be -1. -1 squared is 1. So we have 1 plus 1 is equal to the square root of 2. So that's going to be our radius. Okay, distance between the center point and one of the endpoints, that's the radius. Okay, so with our circle equation, our x minus h squared plus x minus k squared is equal to r squared. We have x minus h is minus -4, so plus 4, squared plus, that's a y. Y minus k, k is -2, so y minus -2 is y plus 2, is equal to r squared, so -2 squared. -2 squared is just going to be 2. Gets rid of the square root. Okay? And we can see the solution here is exactly what we have. Any questions on that?
How do you guys feel about circles in general? Like when it's a circle problem, are you like, pretty good? I don't know what I'm doing.
Well, I used to do the distance formula of the whole
Yeah.
And then do that divided by 2 squared.
That works
But
too.
when you have square root like negative or 2, then it doesn't work.
Yeah.
So,
Yeah. Yeah, it's easier to do it with the center, but yeah. The doing it with the diameter endpoints also works. You just have to divide by 2 after to get the radius. Yeah. Okay, cool. Okay, Emily, I will let you take over for the last little bit.
Thanks. Okay. Can you show me how do I get
Yes.
to question 6?
Okay.
Thank you.
It is. Oh, is it finally working again? Okay. I think if you press all the way at the very top here, you can press this, or let me click this actually, and you can click the eraser,
Okay.
and that's how you erase. And then you can just click that again, and it'll go back to the pen. And you just swipe, or you can tap, and then you can just draw.
Okay.
Yep.
Very nice.
Yeah.
Part 2. Combined functions. Composite. Oh, so hold on. We're already on problem 6. How did we get there?
Oh, it was just counting the problems in the sections before
Okay.
as problems. Yeah.
Okay.
Yep.
So I need to go all the way.
Yeah.
Wait. I was planning on doing problem 6, problem 7, problem 8.
Oh.
This is this, right?
Yeah.
Okay. Great.
Okay.
Okay, it's showing up. Thank you. Okay. All right. Okay, so general rules that we want to go over. Just to remind you, this fancy notation that we have over here, does this erase like that? No, it does not. Okay.
No, it doesn't. You have to
Darn.
click the eraser.
Okay.
And,
Okay. Oh. Okay, there we go. Now I know how to work this. Great. Okay, so that notation that I touched, f plus g of x is equivalent to f of x plus g of x. We can think of that in 2 ways. I can evaluate it just like it's written at the function f of x plus the function g of x, or I can think of the new function f plus g of x with an input of x. Do you follow? Sort of. Okay. Same deal with the subtraction. I can think that I have a new function that is incredibly related to the old functions, but is a new thing, the function f minus g with inputs of x, or I can think of it as I have the function f of x and I have the function g of x, and to evaluate like f of 3, f plus f minus g of 3, I could evaluate it as f of 3 minus g of 3. Following? Okay. Same deal with multiplication, exactly how you would think. For specific inputs, multiply outputs. Like if I specify which number, for general cases, multiply the functions. If I want to know the expression, that's also a roadmap for what to do. I need to multiply the whole function f of x times the whole function of g of x. So those ones are probably just about what you were thinking. And division, same deal. We have to follow the same rules as always. As long as g of x does not equal 0, we're good. If a certain input x causes g of x to equal 0, that means we have a domain restriction for that certain input value. So if I have some function with a denominator of x minus 3, or in other words, my function g of x is equal to x minus 3, and I want the function f of g of x, if that would give me a hole in the domain at x is equal to 3, because I would have a 0 on the bottom. I can write that out if you'd like. Would you like me to write it? No? Okay. Okay, so this is just a review of what that notation means. This is the probably fun new one, the composite function. Yes, it kind of looks like sometimes the O is big, the like circle thing is big like an O or small, but it's always meant to mean f of g of x. That means I'm going to put, like it says, this means we will put our inputs into our function g, then we will put the outputs of that function g into our function f and get our final output. And so that roadmap is really important on several of the questions on the last half of CBE too, because that's how we do them, and it's going to test that you're sure which inputs go where, which outputs go where. So let's get going. So given that I have f of x is equal to the quantity 1 over, over 2x squared plus 1, and g of x is equal to the square root of x minus 3, find find the output of the function f plus g at 4, and f composed of g, that's how you read that little circle thing, f composed of g at 6. So, first still, you can do this however you'd like. I actually kind of don't like this red ink, so hold on. Oh, stop. I like blue. Okay. We're gonna go like this. I'm gonna remember that because of the definition of f plus g, I can go like this. And personally, I think that's going to be faster. Whenever you have a specific input, I believe it is simpler generally to just evaluate the two functions versus creating the new general expression f plus g up here with generic inputs. Because generally it's faster to evaluate numbers, but you can if you want. For this case, I'm going to evaluate it like this. So what is f when x is 4? Well, I have 4 squared, so that's 16 times 2. So 16 times 2 is 32. Okay, 32 plus 1 is 33, so I've got 1 over 33. And g of x at 4. Okay, so 4 minus 3 is 1, and the square root of 1 is 1. Okay, so anyone remember how I can combine those if I wanted to? Oh, I already tapped it. Whoops. You already saw the answers, but if I want to go from the number 1 over 33 plus 1 into one single fraction, sometimes it matters, sometimes it doesn't. Do you remember how?
Yes. 1 is 33 over 33.
Yes, yeah. And that's because I want a common denominator, right? So I just have to find an expression of 1 that has a denominator of 33, and that happens to be 33 over 33. So we just do that. And then we're in business, which is the thing we already saw. Okay, great. Same deal over here. I'm going to write down my definition. Are you guys doing this when you do this problem? Do you like write out like what is the roadmap or not really? Just kind of look at it, just kind of staring at it. Okay, I recommend it because if I have a roadmap, then I can follow it instead of just like I kind of was thinking this and I don't remember what I was thinking when I started the problem, and then you can just like centralize what your brain is doing by what you wrote down. So that means this: f of g of x, f composed of g add 6 means f of g of 6. And I put the spaces there to like indicate parentheses. So let's do it. Anyone want to tell me what g of 6 is?
Square root of 3.
Yeah, because I plug in 6 as x. 6 minus 3 is 3. Perfect. So I've got that now. So now I got to evaluate that. So I'm going to write it out. What is f at the square root of 3? Okay. 2 square root of 3 squared plus 1. Okay, beautiful. I feel like we're probably pretty comfortable with that. The square roots cancel. And if we're not, we can go find help. 2 times 3 plus 1. Okay, perfect. So we've got 1/7. Okay. How do you feel about that? No? Any parts you want me to like re-explain? No? Okay. I think next time I'm going to ask for thumbs. Like, this is great, this is horrible, this is kind of okay. Okay. All right, so same deal. Now we want to find the general one. Let's go for it. So once again, I'm going to write down my little roadmap before I get started. You don't have to do this if you don't want to, but especially as you're practicing, I recommend it. Like, let me just translate that into things that I know I understand. So I want to take the whole output g of x and put it inside the function f of x. So I'm going to do that like this. Like so. Okay. Do you agree with me? Yes? Cool. I think you should. I believe I did it correctly. Okay, so they simplified it a little bit, but technically my answer is correct. You should practice. I actually don't remember. Indy, do you remember? Does the CBE mark that as correct or not?
I think it should, unless it says
Yeah.
simplify.
Okay, so unless you should maybe check us, but as far as we know, unless it tells you to simplify, you don't actually have to do any of the work to get it to what the solution says. You are not required to, because what you have done is conceptually identified that f of g of x is this thing. And the computer knows how to do algebra. It's really, really good at never making mistakes. And so you don't have to like spend your time manipulating it unless you are asked to simplify. Does that make sense?
Oh yeah, just make sure everything is like in parentheses and stuff correctly, because the computer
Yes.
will mess up if you
Yes.
on doing algebra if you don't enter those correctly.
Good caution. Yeah, you have to give the computer all of the instructions, but if you give it all of the instructions, it knows how to do algebra. So, okay, moving right along. Okay, domains of combined functions. So, what do you guys remember about, well, I'll just read it for now. Okay, if and only if, domain of f plus g of x, f minus g of x, and f times g of x. If and only if a real number x is in the domain of f and in the domain of g, then x is in the domain of f plus g, f minus g, and f times g. Okay, kind of complicated phrase there, but what it's saying is, okay, if I have a real number x in the domain of f and g, then that same number will also be in the domain of however I'm combining them, if I'm combining them in those ways. Addition, subtraction, or multiplication. Thoughts? Do you agree? Yeah?
Makes sense.
Makes sense? Okay. So basically, find the domains of f and g and keep whatever they have in common. If it's in both of them, then it's in the combined function. If it's not in both of them, then it is not in the combined function. Okay. So, and the domain of f divided by g of x is different because we have like that added restriction that g of x can't be 0, right? So if and only if a real number x is in the domain of f and g, and in parentheses, g of x is not equal to 0, then x is in the domain of f divided by g. So only difference is we have this added restriction that g of x cannot be equal to 0. So if given input makes g of x equal to 0, that given input cannot be in our domain of the function f divided by g. Okay. Similar deal. Domain of f composed of g consists of all real numbers x such that x is in the domain of g and g of x is in the domain of f. Okay, so if I have an x value that is in the domain of g, of my g function, and when the output, g of x, is in the domain of f, that means that that original x input that I put in f is a valid input of my function f composed of g. There are so many words when I try to explain this with words, but that's what it means. So find the domain and range of g, then find the domain of f, and the domain of the whole composite function will be those that are in the domain of g whose outputs are in the domain of f. That's kind of the summary, that little last bullet point. Yeah.
If the function, either one, f or g came first, if the composite of the inside one, like g in this case,
Yeah.
or f, you would find the domain and range, which would be the notation, right?
Yeah, that we
So-
often write it down with the interval notation. Yeah.
So then the outside function, f in this case, would be, you would find the domain and then figure out the range.
Okay, so the domain of the original function f doesn't actually matter when I'm determining the domain and range of f composed of g. Like it kind of does because it influences what values, like it can give you a guess, but the things you care about are the inputs to g, in this example, like the inside function, which we're calling g of x here. The inputs to g of x, the outputs of g of x, and the outputs of f when the inputs are the outputs of g of x. Yeah?
Yeah.
Okay. Yeah, perfect. Thank you for the comment. Any more comments? Okay. All right. Now we're gonna put it to work because this will help us solidify like what all those words mean. Okay. So let's find the domain of f composed of g of x. And I'm going to do the thing that I keep telling you I like to do. I'm just going to write it down. Okay, so I need to find first domain of G, then range of G, and then range of F when domain, or like inputs, I'm going to say inputs, are the range of g of x. Okay, so anybody want to tell me what the domain of g of x is?
Maybe 2 infinity.
Okay, and with a closed bracket, right? Because the inside of my square root can be equal to 0. So I say do that and then self. Okay, that is the domain. What is the range? Think about what a square root looks like first off. It can grow infinitely. Can I have negative y values though? No? Okay, can I have 0 as a y value? Yes. Okay, so I can have 0 as a y value, I can't have negative numbers, I can't have infinitely many positive numbers. So that means the range is 0 to infinity. Okay. And then we're going to want to look at, nope, we didn't do that yet. Okay. We're going to want to look at the equation for f composed of g to find number 3. So I'm going to write that down real fast. What time is it? Sorry.
5:27.
Thank you. I'll go fast. Times x minus 3. I'm simplifying as I go because the squared would cancel out the square root on g of x. So I want to know what is the range when I have said the inputs are only allowed to be outputs of g of x. And the way I said that the inputs are only allowed to be outputs of g of x is I have put the function in my function. So we're going to find the domain, sorry, the range of this function. Oh, we don't actually need to know. Anyway, I'm going to write this down real fast. And then it will make more sense. Minus 6 plus 1, so that is minus 5. Okay, so now I lied to you, sorry. Because we are finding the domain of f composed of g of x, I don't actually care what the range of f of x when the inputs are the range of g of x. I care what the domain of f of x is when the inputs are the outputs of g of x. So, oh wait, okay. So I need to look at this function and this function over here and know what its domain is. And that would give me a hole somewhere, right? And I only need to be concerned if the denominator is equal to 0. So I can do that real fast. I know that it can't be equal to 0. So x can't be 5/2. Okay, so, which is equal to 2.5, right? Okay, so now how do I put those together? I don't actually have to have this written down, this number 2 step, but it's helpful like for me sometimes, and in other questions it might be useful. But to know the domain of f composed of g of x, my g of x function is limited by its own domain, and then the f composed of g function is limited by the expression over here. And so I just know that this is not a valid input. But because I need to combine these two, if I put them on a number line, 2.5 is less than 3, right? So 2.5 is already not allowed in this domain, and so that domain expresses the entire domain of f composed of g of x. So we're good. Questions about that? I gotta put them together. Basically, find the domain of g of x, make sure that the domain of f composed of g of x, when you make the expression, doesn't add any restrictions to my domain. We cool? Okay. 7. This one is where it gets fun. Okay. And it's fast. So we have this function. It's defined in ordered pairs, but we're cool with that because we know our definitions. And we have this function g, also defined by ordered pairs. Okay, I want the ordered pairs for the function f times g. So just reminding us, that can look like this. That's a g. Okay, so I'm going to write out some ordered pairs. I'm going to make a group of ordered pairs. 2. Okay, so I'm going to do the first one. I need to know that the x input is in both f and g. So the first x input in f is -2. Hey, look, I have another -2 in g. So this input, -2, is in both f and g, so it will exist in the function f times g. So how do I do that? Well, I need to multiply what the output is in f with what the output is in g. So 2 times 3 is 6. So when the input is -2, in the function f times g, the output is 6. Okay, next one. I'm going to look. The next one in f is -1. I have that same input, -1 in the function g. Anybody want to tell me what the ordered pair is in the function f times g?
At -1, it's -8.
Yes, exactly. Can you tell me what you did in your head?
4 times -2.
Exactly, thank you. Okay, whatever shall I do if I have an input in f that is not, oh, but it is, it's just in the wrong order. Okay, I need the input 0, and I found another input 0 in g. So I know that the x input exists, well, some y output exists because the input is in both functions, and then I'm going to multiply them both together. 6 times -1 is -6. Beautiful. Okay. So now I get to say this, on f at least. What happens if I have an input in f that I don't have in g? Does it exist? No. Why not?
It doesn't.
It doesn't. Okay, I trust you. Yeah. It's because I need both of the inputs to exist in both functions for that to make any sense. Can I have an output if I don't have an input? Like if I don't give you money, you can't give me products, you know, like it doesn't work. I need an input to have an output. So when I don't have an input in one of the things, my expression is incomplete and the answer is does not exist. So, okay, so we're done with that one. I see an input of 6 and another input of 6, so we're in business. And 10 times -3 is -30. Awesome. And because I already checked, like, oh, there's no -3 in f, we're good. That's all of the ordered pairs that are in the function f times g. So I kind of wrote on top of it, but I think we're right. Okay, same deal. I want you guys to kind of drive on this one because I'll give you the roadmap, and it works exactly the same way. I'm going to do one example, and then you guys are going to help me. So I need to go like this. I have an input in the function g that gives me an output that is an input in the function f. So I'm going to check. In function g, I have an input of -2 that gives me an output, I'm going to do a circle, of 3. Do I have an input of 3 in f? Hey, look, I do. That gives me an output of 8. So we're in business. At inputs of -2, I have outputs of 8 in the function f composed of g. Okay, let's start with this one. Walk me through the checking process. Could you be the first one?
-1 equals -2,
Okay.
so the function -2.
Awesome, yes. Okay, now let's do this one. At -3. Can you walk me through the checking process?
I'm still watching for a second.
Okay, Can you walk me through the checking process?
At -3, the output's 1,
Uh-huh.
but there isn't output of 1, or an input of 1
Uh-huh.
F, so it wouldn't be included.
Exactly. Perfect. Thank you. Okay. I'll do the next one. At inputs of 0, I have an output in G of -1. Oh, I broke my own rule. I have an input of -1 in F, so we're in business. And so at inputs of 0, my output in the function f composed of g is 4. Because I went 0 has an output of -1 in g that matches with the input in f, which gives me an output of 4. Okay, let's do this one. Do you want to walk me through it? You got it, you got it. So I circle the -3.
Isn't one, is there?
There isn't one. Yeah. So I would start, I'd be like, okay, I have an input of 6, I have an output of -3, then I search, okay, I'm not seeing any -3s in these inputs. So I'm good. There is none. Okay, so that's my whole thing. Oh, it's right on top. -2, 8. Yep, -1, 2, 0, 4. Okay, we're cool. All right, now we're gonna do this for some functions. Actually, let's see if they're the same. I might cheat. They are the same. Okay. So, oh no, they're not. They're different orders, which is different. Okay. So, like I said, when I have a specific input, I think it's generally faster to just evaluate the input. But I'm gonna write my roadmap, which as it gets more complicated is even more helpful, I think. Like this. Do you agree? Yes? Cool. Okay, so I'm going to plug 2 into h of x. And actually, I'm going to write parentheses for now. Okay, 9 minus 2 times 2 squared. Okay, so 2 squared is 4, times 2 is 8. So 9 minus 8 is 1. I'm going to do this on a different line. So now I'm going to plug 1 into G. And you could do these as separate problems, but I recommend, I think this organizing of my work is a good way to not get confused. So 1 squared is 1, times 2 is 2, plus 8 is 10. Okay. Sorry, that's equal. So f of 10 is what I want. Now I'm going to plug it in. So 1 over square root of 10. Oh, beautiful. Okay, now we're done. Do you want me to gesture at anything?
So you're just going from right to left, pretty much plugging in.
Mm-hmm. Yeah, that's kind of how the notation teaches me to do it. Kind of like I'm going from inside to outside more than from right to left, because this function is kind of like nestled inside all of the parentheses. And when we talk about like function notation like this thing is the input. And this whole thing is called the output because it's dependent on what is my input.
So it's 2 into H, whatever that gives you goes into G.
Yeah.
Whatever that gives you goes to F.
Exactly. Yeah. Okay, awesome. Okay. All right. So does anyone want to tell me what my roadmap is? Like just say the letters and then say parenthesis where they go? If not, it's okay.
F of X.
Mm-hmm.
And that's in parentheses of H of F of X.
Okay.
And then G of H of F of X.
Beautiful. Okay, that works. For some reason, when I do it, I tend to like write the letter that comes first, opening parenthesis, the next letter, opening parenthesis, and then wherever the X goes, and then just close all of them at the end. But what you did was beautiful. That totally works. Do it that way if your brain works that way. So, okay, that's our roadmap. And now I have to do some kind of more annoying algebra, but you can just write it all out if you want. You don't have to simplify it. So first G. So I'm going to make these parentheses really, really super big because I'm going to try and not simplify it first. I really don't like that I don't have an eraser on the other side. No, go away. Okay. I'm gonna make the parentheses really super big. Squared plus 8. Okay, so this big open gap is where the x would go, but I'm gonna leave it open because I need to put h of f of x inside there. So next I have 9. I'm gonna make them different colors. Actually, we're gonna do this super fancy. Erase. No, that was big. Okay. Okay. Blue is, oh, okay. G of h of x, opening parenthesis, yep. So that's G. Now we're gonna do h. 9 minus 2 of x squared. And now we're going to do, I'm gonna make it blank. Now we're gonna do f of x, which is a little smaller, thankfully. Okay. Do the colors kind of help? You probably are getting it already, but just to show. And if we simplified it, it would be that thing. Do you want me to go through the process of simplifying a little bit? I would be happy to. Okay. So let's start with the inside. To square something, if I have 3, ooh, actually, do I know this? It's 909, yeah. Yeah, okay. So this is true. I do things with numbers sometimes when I can't remember. So if I'm squaring a fraction, it's the same thing as having the numerator squared over the denominator squared. Is that true, India? I think it is.
Yeah.
Okay, thanks. So that's what I'm gonna do here in the middle. 9 minus 2. 1 squared is 1, and x squared is x. Or sorry, square root of x squared is x. Right. And that's still inside squared, and that's 8. Following? Okay. So next thing. That's 2 times 1 over x. So I'm just gonna rewrite it actually because I'm lazy today as, ooh, that's a very small eraser. Come on, guys. As 2 over x. Okay. And then these parentheses are squaring this thing. So I'm going to do that in a little mini problem up here. So 9 minus 2 over x squared is equal to 9 minus 2x times 9 minus 2x. Okay, so 9 times 9 is 81. 9 times negative 2 over x is negative 18 over x. And same deal, negative 2 over x times 9 is negative 18 over x. And negative 2 over x times negative 2 over x is positive 4 over x squared. Okay, so that can come down to 3 terms. What's 9 times 4? 36? Okay. Yeah. Okay. All right. And so that's all being multiplied by 2, and we're adding 8 to it. So, because it came from inside these parentheses. So it's all being multiplied by 2, and then we're adding 8 to it. So I'm going to multiply it by 2 as I put it back in. 2 times 81 is, ooh, probably 170.
62.
Thank you. 162. Close to 170. 2 times 36 is 6 times 12. Okay. So 6 and 72. Thank you. Yep. 72 over x. You can be good at math even if you're not good at arithmetic. It's okay. And adding, I need to multiply 2 by 4 plus x squared still. That is 8x squared. And then 8 over x squared. And I'm still adding 8 to it, like so. Okay, and 62 plus 8 is 170. We cool? Okay. All right, so now we want the domain of this thing. Okay, so once again, roadmap. First step, like so. I think there's 3, yeah. Okay, I need to know the domain of f, and then I need to know if the function h of f, h composed of f, adds any restrictions to that domain, and then I need to know if the function g of h of f adds any restrictions to that original domain of f of x. So my original domain of f of x is based on the fact, is going to be influenced by the fact that there is a square root of x in the denominator. So when something is in the denominator, it cannot be equal to 0, and when something is inside, and when the variable is inside a square root, it cannot be negative. It must be greater than or equal to 0. So because we had both a greater than or equal to 0 and we had a cannot be 0, our total restriction is just greater than. X must be greater than 0. Do you agree? Yes, maybe? Are you sure? Okay. Okay. I like to be like pushed back a little bit. Like if I didn't just tell you that, would you still believe me? Okay. So I'm gonna write it up here. The domain of f of x is x has to be greater than 0, or in our domain notation, that's like this, right? Oh, sorry. Greater than soft parentheses. Up to infinity. Do you agree? Okay. Okay, so now I need to know what is h of f of x. And I believe I need to create the whole expression in order to know that, I think.
Yeah.
Yeah. So we're going to go like this. Up over here, 9 minus 1 over square root of x squared. And then it's going to be helpful for us in this case to simplify it a little bit so we know what we're dealing with. 1 squared is 1. The square root of x squared is x. Okay, so the domain of this expression right here is just that x can't be 0, right? That's the only place I have inputs. And we already know that. For our current domain, the current guess for our domain of g of h of x is that the domain is the domain of f, and x already can't be 0, so we're cool. Okay, now I need to know what is g of h of f of x. And because we already found h of f of x right here, I can just plug this into g, and we're okay. I'm gonna do it over here. H of f of x. Okay, so 2 times 9 minus 2 over x squared plus 8. Okay, so same thing. I need to square that, and I'm actually going to cheat and come back here. 81 minus 36x plus 4x squared. To square those real fast. And then it still simplifies to the same thing because we have the same signs and all the stuff. So just write it out. I think it's 72, right? Yeah. Okay, so same deal. The only domain restriction for that function, for that expression, is x cannot be 0. We're already prohibiting that. So the domain of the function g composed of h composed of f is the same, actually. We found out that it's the same as the domain of the function f. We didn't know that at the beginning, and that won't always be true, but in this case it is. So that's your answer. There we go. Oh, I didn't even finish it. Shoot. Okay. All right, so inverse functions. What do you guys remember about inverse functions?
They reflect across y equals x.
Ooh, that's a good one. Yeah. So when I have, ooh, that is super not straight, but whatever. Yeah. When I think of the line y is equal to x, if I have some function like this, it will be flipped over that line. Any function will be. Okay. This thing right here is kind of fun to know, but it's when written, a function must be a bijection. It's sometimes hard for me to remember what it means. So that's why the parentheses are helpful. A function to have an inverse, and if an f and g are inverses, if and only if f composed of g is equal to x, and g composed of f of x is equal to x for all x in the domain of f and g. So meaning, a function must be a bijection, or in other words, every output has a unique input. So like the function x squared, y is equal to x squared, is a function because every input has one and only one output, but it is not a bijection. It does not have each output does not have a unique input because each output has exactly two actually inputs, because those horizontal lines I just drew hit the graph in two places instead of just one. That's also sometimes called the horizontal line test. So if I wanted to make the graph of, the equation y is equal to x squared, like make it possible for y is equal to x squared to have an inverse function, I would need to say for x is greater than or equal to 0, because then it would just be this side. And that does pass the horizontal line test. Okay, all right. So we can find inverse functions by switching y and x in the equation and solving for y. So in this case, if I wanted to find it, I'd have to remember my domain, and we're going to do this in a second, but I would start by going like this, and then solve for y. Okay, given a graph, you switch the x and y coordinates in order to graph the inverse, and that's what you were talking about. We're just going to flop the coordinates in order to reflect over the y equals x line. Okay, determine an expression for the inverse function of f. Let's go. So I want f inverse, which means I want to know what are the outputs when all of the inputs have been flopped with them. So we go like this. X is equal to 5 cubed root of 2y plus 2 minus 6. And a lot of my students in recitation are comfortable writing this, and then they're like, and now what do I do? So and I always ask them, like, what is their goal? Well, right now, I want to be able to write this thing that I've just written down in a y is equal to stuff with x form. So that means I need to get the term that has y in it by itself. I want to isolate it. So I'm going to add 6 to both sides, and then divide by 5 on both sides, and I'm going to do it super fast. And then to get rid of in quotation marks, that cubed root, I need to cube both sides. So I'm going to do that without writing it necessarily. And then I can subtract 2 and divide by 2. Minus 2 all over 2 to get y. Questions? I went through the algebra fast, I know, but
What's your final answer?
that is the expression for the inverse function of f. Yes, that's it. And I know that because I started with flopping the variables. You could write whatever letter you want there. It's just probably faster to write y instead of f inverse every time.
Did you accidentally forget to write the cube on top of that?
Yes, I did.
Okay.
I totally did.
Just make sure.
Thank you. Any other mistakes? I do those. Okay, awesome. And it's super right on top, but that's our answer. Okay, domains and ranges. So because of how we have defined what it means to be an inverse function, the domain of the original function is literally the same thing as the range of the inverse every time. And the range of the original function is literally the same thing as the domain of the inverse every single time. If the inverse exists, it has the same domain as the range of the original. I might have said that backwards, but it's up there. The range of the original function is the domain of the inverse. So we can find the domain of the inverse just like we would find the domain of any other function. However, we then need to check if our original function imposes any restrictions. So what that means is the domain of the inverse is findable from the equation of the inverse, but I need to make sure that the values that I would be inputting into it are even allowed to be inputted based on the domain and range of the original function sometimes, and I'll show you what that means. So, using interval notation, write the domain and range for the inverse function of f. So, like I just said, we might want to know what sometimes the easiest way to find the domain and the range for the inverse function is looking at the function itself and knowing that they are inverses of each other. So, the domain of f of x is what? What do you think?
Anything greater than -2.
Okay. Why do you say that?
Because oh wait, no, that goes through. Huh?
Yeah. So this is a cubed root. Can I have negative outputs from a cubed root? Yes. So it doesn't actually impose any domain restriction. It goes forever both ways. The range might have a restriction. I don't think it does. It's kind of hard to tell from this equation. So what I would do usually is I would know the domain is negative infinity to infinity. And I'm not quite sure what the range is. I think it's infinite because I think it would grow forever in both ways. But if you didn't happen to know that, you can find f inverse, and the domain of f inverse is the range of f of x. So, and this right here is the range for f inverse. So, range of f inverse, we have already found, it's this. Okay, and then we just found, I think right here, yeah, the expression for f inverse of x. I'm going to rewrite it. Ooh, that's a lot of numbers. Let's see. I think plus 6 over 5 cubed minus 2 over 2 cubed minus 2 over 2 plus 6 over 5, yeah. Whoa. No, stop. Okay, so that's our function. Does this have any domain restrictions?
Can't be -6.
Why not?
Because you just have 0.
Mm-hmm. But what would that evaluate to?
2 over 5.
You didn't say it doesn't exist, like it blows up.
Well, you would assume that for x over 1 or 1 over x that there's those slight mishaps where a number doesn't just have any value.
Yeah. So you're kind of imagining graphs like this, right?
Yeah.
Like that. That's good. On certain graphs, those exist. I would put forward that does not happen on this equation. Yeah, because let's think about it like what you just said. You said, okay, what if I put in a -6? That means I get -6 plus 6 over 5, which is 0, right? Do you know how to tell me what 0 cubed is? What's it equal to?
0.
Yep. What's 0 minus 2?
-2.
And what's -2 divided by 2? -2 divided, yes, -1, good job. Okay, so you've just told me that if I plug in -6, I get a -1. I never tried to divide by 0. Do I have a domain restriction when I have -6 as an input? So it does create a 0 in that numerator, but it doesn't cause any problems right here because I know how to tell you what number it evaluates to. So this f inverse does not have does not have a domain restriction. So the domain of it is negative infinity to positive infinity. But I'm so glad you said that because so many students will think like, well, that's what we cared about before. It probably matters here too.
Yeah, I've seen the problem come up like 7 different times.
Yeah.
And it's always different. So
Yeah. Yeah, we got to think about like, okay, so when I have input, when I have a certain input, does it cause me a problem or not? And in this expression, it doesn't cause me a problem to have a negative 6. If that x plus 6 thing were in the denominator somewhere, that would be a big problem because I can never divide by 0. And that would cause me a domain restriction. Okay. So now we're good. That's the domain of f inverse. And we already found the range because we found the domain of the original function. So now we know. Okay, the last one, we're almost there. Determine an expression for the inverse function of f inverse. So I want the inverse function of f. Didn't we do this just barely? Determine an expression for the inverse function of f. Yeah, we did. Okay, we did that already. We know how to do that. We switched the x and y. Okay. Using integral notation, write the domain and range for the inverse function of f. We also just did that. Negative infinity to infinity is the domain. The range, negative infinity to infinity. Because we found f inverse, and f. Oh, sorry. I definitely misread that. It's squared now. Sorry, friends. It's different. This is very important. Oh, my pen on my laptop has like a different eraser. Okay. All right. So definitely misread it. Let's go. Come on. Thank you. There we go. Okay. So now we're doing it for the squared version. Very important. Okay. So very devious of them to like just hide that right after the other. But this is a good lesson. We got to be detail oriented when we're doing these CBEs. So I need to know the domain. So I know that the insides of square roots cannot be negative. So it's got this thing, the inside part of the square root, has to be bigger than 0, bigger than or equal to, because it can't be negative. So x can't be, or sorry, it has to be bigger than or equal to -1. So I subtract the 2 to the other side, then I divide by 2, that gives me -1. Okay, that is the domain of my function. Oh, and I'm kind of jumping ahead, I think. Yeah. But it's going to teach us something. So the domain of f is the range of f inverse, right? So already I can write that down. I can say, whatever it was, x is greater than or equal to -1. Because that's also the range of f inverse. Now I'm going to finish finding the expression for the inverse function of f. So what's my first step?
Which the variables?
What should I write down?
5 times the square root of 2 times y plus 2 outside minus 6.
And what's it equal to?
X.
Yeah, x.
Yeah.
So you said it out loud, but it needs to be equal to x because I'm just flopping them, right? I put y where I saw x, and I need to put x where I saw y. We don't usually write it like this, but you could, because we're kind of emphasizing like the function is a function of f when we write it like this, and we're saying like outputs exist when we write it like this. But they're both valid. Okay, so now we want to solve this thing to have the inverse function of f. Here we go. I want, remember, what's my goal?
Isolate y.
Yeah, I want to isolate y. Okay, so I'm going to add 6 to the other side, then divide by 5. Okay, now I'm here. And then what do I have to do?
Square.
Yes, exactly. And the solution's already up, but it's fine. Okay, and now what do I do?
X2 and divided by 10.
Exactly. Okay. Very, very similar, but slightly different. And I think that's the point they're making. We have the same expression for f inverse, whether it's a cubed root or a square root-ish. But we don't have the same domain and range. So, very important. And, we're going to need this in a minute because it's going to ask us, what is the domain of the inverse function of f? We could look at this and determine what its range is, but sometimes that's a little trickier. And if you haven't had a lot of experience with finding the range of functions, it might be hard to just look at and know. But we are very practiced at finding the domain of things. So if I have f inverse, that's what this is, I can find its domain. And like we said, also does not have any domain restrictions, this one, because if I plug in -6, I get a number that I can work with. I never am dividing by 0, so we're good. Okay, questions?
Wouldn't the domain be?
Oh, sorry, yes, I made a mistake. Yeah. So it's asking for the domain of the function of f, my bad. So I need to look over here. Whoop. All right. Okay, domain of the function of f. That was my bad. Okay, so I care that the insides of square roots cannot be negative because it's a square root here. So x has to be greater than or equal to -1. Am I doing this right? Yeah. And then, why is it -6 for the function f? Because we've got the inverse, we're all good. And oh, that's funny, I even found it right here. Okay. Main. I feel like we've got an error right here because it looks like it's trying. It's like 2 errors actually.
Wait, go back to the last one.
This is the problem I incurred on the CBE too.
Mm-hmm. Yeah. So this is where like the definitions really matter, and sometimes even the teacher gets mixed up, and they have to remember. Oh no, I meant that thing, not the other thing.
Oh,
It's asking for the domain and range of the inverse function of f. Okay, we're fine. The inverse function of f.
yeah, so.
Which is the domain of f of x is the range.
Yes.
And then the domain of the inverse function, which is over here. But that doesn't have any restrictions.
Oh, yeah, the range
But
is
it comes
weird.
from
It comes from
the other one.
range of the original.
So we have to consider.
Yeah.
Apparently I'm slow today. Yeah, I forget to follow my own advice. Yes, we have to consider the restrictions. I forgot. So when the original function has valid inputs is when x is greater than or equal to -1, right? And so that means the inverse has outputs that have to be greater than or equal to -1. So we can kind of like make ourselves a little baby problem. I don't know why I'm doing it on this slide, but that's what we're going for. Yeah. And then kind of play with it. So I know that the outputs need to be, and I have it written right here, the outputs, because for the inverse function, the outputs are y, but they come from the x of the f of x. The outputs need to be greater than or equal to -1. So that's what I need to put right here. Greater than or equal to, sorry, other way. Greater than or equal to -1. Okay. Like so. Okay, and then I can solve that. So multiply by 2. Add 2 to both sides. I'm going to come up here. Sorry. Which means it's 0. It's less than or equal to x plus 6 over 5 squared. And we would need to do this whenever there is a domain restriction on f to make sure that it's not causing any domain restrictions on f inverse, even if you couldn't see them.
So the equation from earlier would imply that -6 cannot go into the.
Yes, that's why. Yeah, thank you. And I'm really, really glad we figured that out, because that's why it kind of does matter, even though I was very adamant about, in that one specific case, why it doesn't. Okay, so now I need to take a square root. And I think we're still good. Yeah. Multiply by 5 and subtract 6. Okay. Which gives us our domain restrictions. X must be greater than or equal to -6. All right. Okay, that was a very long and windy path, but how are you feeling?
Pretty good.
Okay, so just as a recap, to find the domain and range for the inverse function, I can find the domain of f, that is the range of f inverse. Then I can create the expression of the inverse function of f, see if it has any restrictions, and then check that the domain restrictions of f don't cause any restrictions on the domain of f inverse. So, ta-da! Hooray! Okay, the graph of f is given, graph the inverse function of f. This one's really fun because, like we noticed, we just need to flop the x and y coordinates. So I've got 0, 8, 1, 5, 2, 4, and 5, 2 on the original graph of f. And then I come to the inverse where I just flop them like this. Because we're kind of thinking about a reflection. Whoop, I can graph that better. Over the y is equal to x line. So let's plot those points real fast. I've got 8, 0, 5, 1, 4, 2, and 2, 5. Like this. Okay, and we can see that symmetry. Okay, all right. So that is the end, looks like. Yes? Okay. We made it! Okay, and we're always here for more help. You can come into the Aggie Math Learning Center in the Animal Science Building, room 119. Send emails there, all the things. Visit our YouTube site for more